As mentioned earlier, there have been cases involving loss of control in icing conditions due to unexpected stalling at speeds considerably higher than the normal stalling speeds, possibly accompanied by sudden rolling. Control can be lost as a result of a contamination-induced stall, the onset of which can be so insidious as to be difficult to detect until it is too late. The following advice may help you to recognize and avoid these gradual stalls, or recover from one if it does occur. First, a loss of performance in icing conditions may indicate a serious ice build-up, possibly unseen, which is causing a gradual loss of lift and increase in drag. Such a build-up can cause the aircraft to stall at about 30% above normal stall speeds. The longitudinal characteristics of an icing-induced stall may be so unobtrusive that the pilot is unaware that it has occurred. A stall warning system, normally triggered by angle of attack, may not be activated by a low alpha stall, but Buffet may assist in stall recognition. The first clue may be a roll control problem, manifested either as a divergent roll oscillation or a wing drop. A combination of roll oscillation and onset of high drag can cause the aeroplane to enter a high rate of descent unless prompt recovery action is taken. If a roll control problem develops in icing conditions, the pilot should suspect an icing-induced stall and take immediate recovery action. The anti-icing system, if fitted, should have been on prior to entering icing conditions, in accordance with operating procedures. If not, it must be activated immediately, and consideration given to leaving icing conditions by track or level adjustment. The tailplane is an aerofoil, and because it is thinner than the wing, will tend to accumulate ice sooner and more quickly than the wing, but with similar effects. However, the tailplane, often an inverted aerofoil, usually produces a downforce. So if it stalls, the loss of downforce will cause a pitch down, with at least a temporary loss of control. Stalling of an ice-contaminated tailplane could be precipitated by the lowering of the flaps, which increases the downwash over the tailplane and consequently alters its effective angle of attack and takes it beyond the critical angle in a negative sense. It should be borne in mind that the tailplane will usually be producing downforce, which is lost if the tailplane stalls. In the event of a sudden pitch down when lowering flaps, the initial recovery action is to retract the flaps, reducing the downwash. Heavy rain, whilst not as hazardous as its freezing cousins, ice, frost and snow, can also have a detrimental effect on stalling speeds and drag. The rain will form a film on the aircraft's surface, increasing the weight, and therefore the stalling speed slightly. As the film of water runs back over the wing, it will distort the profile, roughen the surface, and distort the airflow over the whole aircraft. CL max will decrease, increasing the stalling speed. The surface film will increase interference, profile, and form drag. The approximate overall increments are, for light rain, 5%, moderate rain, 20%, and for heavy rain, up to 30%. This extra drag increases the thrust required. A further consideration, which does not in itself affect stalling speed, is the impact of heavy rain. Lost momentum will require more thrust to maintain speed, and the rainfall will tend to push the aircraft downwards, in much the same way as microburst wind shear, with which it may well be associated. With the conventional layout of the rear-mounted tailplane, the wing stalls first, and longitudinal stability and control are maintained. On the tail-first canard layout, if the wing, the main plane, stalls before the foreplane, then stability will be lost. But if the foreplane stalls first, then control will be lost, and the maximum value of CL is reduced, since both foreplane and main plane are lifting surfaces. In the next lesson in this series on stalling, we return to conventional aircraft and the topic of spinning.